that's kind of what mastering physics tries to do, is like step you through easier questions, like try to show you each part as it builds up. But I think because it's, like what it will do, it basically takes a problem, you got this whole problem, and it'll say, well, here's this chunk, here's this chunk, here's this chunk, here's this chunk. And it'll just kind of spoon feed every little piece to you.
Yeah, and then it has one that incorporates all of them.
Right. So instead, you kind of want to have your problem over here that you're looking at, and then go back to the exercise ones that you'll have to do maybe this much of it. And you practice doing this much of it a few times. Then when you get back over here, you're like, oh, wait a minute, I recognize this part. Like mastering physics, they recognize it for you. When they break it down, they recognize it for you. And they're like, here you go, here it is. You don't get practice actually like recognizing that that's the same piece that you've just been doing. And then you say, oh wow, I've done this part already, and I've done this part, and well, here's a little bit, it's a little bit new, but I can figure out a way to do it. And it kind of works out. So
Okay.
as far as like learning it, I feel like mastering physics it has the idea right. I mean, it wants to step you through it and then give you a chance to try it on your own, but it doesn't give you a big enough piece to do on your own.
Right.
Like it teaches you the concept and then gives you a big problem. And I don't know.
Yeah, my pre-calc class last semester, Brother Starton used to give us like 20 or 30 problems a day to do. But, you know, when you're required to do them every day like that, then you end up learning it. You know, whereas it's not required, I just don't have enough self-motivation to.
And I'm sure that those problems weren't like big, long problems.
You know, he'd do the basic ones. He wouldn't throw anything at us that would, you know, confuse us, because he wanted us to understand the concept.
Right.
So we'd have to do all these basic ones, and it was repetition, and, you know.
So typically what you'll see in like physics classes, and even if you go further along, because you're a mechanical engineering major, right? Yeah, so you'll get into like statics and dynamics, and those classes, they'll give you 4 or 5 questions total for a homework assignment, you know. And those 4 or 5 questions are pretty complex. They'll take 45 minutes, an hour, as long as you know every concept already. But if you don't know every concept, they can take 3-4 hours, you know. But it's good to just take some time and do what your teacher did and assign yourself some problems to do that'll take you 20 minutes and give you a better basis.
Yeah, you know, and I think that's probably my biggest problem is I don't have enough self-motivation to add on to my workload.
I know.
I mean, I'm already pushing midnight every night anyway with the homework that is required, so that's what kills me, you know. And I know, like, in my mind, that makes total sense, that if I get more experience doing the problems, then I'll understand it better, but,
yeah,
you know.
That's kind of where, like, the grade-driven, you know, achievement-based learning is it kind of falls short, because they have all these assignments and these grades that's the goal. You know, you get to the point where you're like, I'm not learning it very well, but I need to get everything done.
Right.
And so instead of, when people start to feel like that, instead of it letting up and saying, well, don't worry about your grade, just learn, it's the opposite effect.
Right, you know, and it'll just come down to time. If I just had an extra day every week to plug in all this extra stuff, that would be the solution. But, you know, I don't know. Yeah. There's I got a calculus test coming up. It's got that same rocket question that we did on the board. Or an example similar to it. And the teachers, Brother Goodself specifically said, practice this one because it's going to be one like that on the test. And I was going over it, and I'm still a bit sketchy on that. Let's see here.
Okay.
find that example. I wrote it out here. Okay. Example 3.4. But yeah, we did this on the board the other day, and I understood it as we were going over it, but as I was looking over it in here, maybe it's a little different. Let's see.
Here you're talking about, we talked about a rocket problem and then the calculus book has one.
Yeah.
Well, it's calculus-based physics, so I'm sure that it's similar. So we can talk about it for sure.
If this isn't your, let's see here, if this isn't physics related, I'll just say it for the shooting center. All right, example 4. Okay.
There you go.
So yeah, it's not necessarily a rocket, it's a rock being blasted up in the air, but basically same concept.
Okay. So yeah, this is kind of physics related. So 160 feet per second, height of S equals. So you got S equals 160 T. What's your equation?
Yeah, S equals 160t minus 16t squared feet after t seconds.
Okay. So T in seconds. And it's saying that S of 0 is equal to 0 feet, right?
Yeah.
So basically, if we were to look at this in the physics form, right, we would have this picture and we'd say, well, here, it came back down like this. We would say this is point 0, so we'd call it Y, but we'll call it S for the sake of this. So S of 0 equals 0, velocity of 0 equals 160, right? That's what they said.
Yeah.
And then times 0 equals 0.
Mm-hmm.
And then we'd come up here and we'd say, well, there's some acceleration. I'll show you where that comes from. That problem asks for something different, but we'll get to this. And then it'll say what's the maximum height, right? Is that what it's asking? How
Yes.
high? What are the velocity and speed of the rock when it's 256 feet above the ground on the way up or on the way down? So what's the speed at 256 feet? So we've got this S1 equals 256 feet. V1 equals what? T1 equals what? And then we've got this point up here, S2. That's the maximum height, right?
Mm-hmm.
V2.
Is-
T2.
And the velocity, because it was just an explosion at the bottom and there's no acceleration up, it's always just going to be gravity, right?
Yep.
So,
So let's do it the calculus way, and it'll just blow your mind.
okay.
Okay. So what if I told you that this is our position equation?
Okay.
So I'm going to say, if we were to call this, do this exact same equation, we said y final equals y initial plus v initial t minus 1/2 a t squared. So that would mean that y final, do you see any constants in here?
I guess I don't understand what a constant is.
Oh, so a constant is anything that isn't tied to a variable.
Nope.
So there's no constants in here, so that means that our y initial was 0. Is that true?
Yeah.
Yeah, okay. Plus v initial times t, so which number is next to a t?
Well, both of them, but 160.
Yeah, a t versus a t squared.
Okay.
So 160t, so now we're saying our initial velocity was 160.
Okay.
Isn't that exactly what we said
Yeah.
at the that's what the book says even,
Right, yeah.
okay? And then minus 1/2 AT squared. So if this is minus 1/2, and it'll give us that, what's acceleration? Or wait, no, plus, excuse me. Plus 1/2, this is our position equation.
Okay. 32.
So we find out the acceleration is negative 32 feet per second, t squared. And if we simplify this, that gives us y final equals 160t plus, or minus 16t squared. So we could have found this out if we were just the physicist. If they gave us the physics version of this problem, we could have plugged in, we already know that, we already knew this equation, so we could have plugged in y final is going to be equal to y initial, which is 0, plus v initial, which is 160 times t, plus 1/2 a. A would have been given to us as the acceleration due to gravity, was negative 32.
Mm-hmm.
Could plug that in there, okay?
Okay.
So that's how we would have gotten this equation in the first place. And then we would have said, we would use our physics equations to solve the rest of it. Instead, let's do this. Let's do it the calculus way. So this is the position equation, so how do we find the velocity equation?
The derivative of that.
Yeah, so this is going to be velocity equals, what's the derivative of this part?
160.
160. What's the derivative of this part?
Negative 32.
T?
T, yeah.
Yep. Wow, okay. So let's look at our version of it. So V final equals V initial plus AT. That's our equation, right?
Mm-hmm.
So V final, what's our initial velocity?
0. Oh, 160.
Yeah, so it blew up immediately. It was going 160 miles an hour. What's our acceleration?
Negative 32. T.
So it ends up being this, which is the same.
Mm-hmm.
And then they say, well, what's the acceleration? The calculus book says find the acceleration.
Uh-huh.
So how do you find acceleration from velocity?
Take the derivative.
So acceleration equals, what's the derivative of that?
0.
0. The derivative of that?
Negative 32.
Oh, look at that. Acceleration equals negative 32.
Okay.
And we could have found that out just by looking at the physics of it. We know that the acceleration due to gravity is going to be negative 32 feet per second squared.
So, okay. How does that work with gravity? Is gravity negative 16 t squared or negative 32?
So gravity is negative 32. Remember how in this equation it's actually 1/2 acceleration times time squared?
Right.
So right here, this is where the 16 comes in, is because you have a plus 1/2 a t squared.
Okay.
So 1/2 of a is going to be negative 16.
Okay. So gravity is negative 32 feet per second.
Yep.
Squared.
Feet per second squared. And the units, as far as calculus goes, so this is feet, right? And t is in seconds. And then this is going to be ds dt, which is s is in feet, t is in seconds. So that gives you units of feet per second.
Okay.
And then you take dv dt, which is equal to a, which is also equal to d squared s over dt squared.
Where did that come from?
So acceleration is the derivative of velocity, so you take dv over dt.
Okay.
So you have, this is gonna be in meters per second, this would be in seconds. So that gives you, oh, feet per second, excuse me. That gives you feet per second squared. And then this is, you see that, you find out later that that's kind of like the notation for second derivative.
Okay. Oh,
And that
right.
would be in feet. And then dt squared, that would be seconds squared.
Okay, yeah, I remember that now.
So that's where the units come from.